All right, students, let's try another solution. This is from the harder book, the university physics book. It's number 48. And it looks harder, and I decided to print it up because of the picture, and I thought it would be easier to kind of understand the question if we look here at the picture. But it says a projectile is shot at a hill, the base is which 300 meters away. So they've got 300 meters away. The projectile is shot at 60 degrees, so there it is, above the horizontal with an initial speed of 75. The hill can be approximated by a plane with a slope of 20 degrees, so here it is, to the horizontal, relative to the coordinate system shown in the figure. Well, let me pause there. Looks like they put the origin right at the launch point. Okay, that's good. The equation of the straight line, and so they're saying that this equation right here indicates this hill that it's going to land on. Where on the hill does the projectile land? All right, so I hope the first thing you do is split your paper in two and say, let's do some calculations for x and for y. And maybe even write out what you do know, like the initial position. And in this case, both x and y are 0. That is the advantage of picking the origin as the launch point. Okay. Like I said, that's usually a good place, but it's not always the best. Sometimes there could be better ones. But I think in this case, that's the best one also. And we got to follow their lead anyway. So there's the origin. Now, the other thing with the acceleration, it's a projectile motion, so we've got 0 acceleration in the x direction and negative 9.8 in the y direction. Maybe the step that you're getting pretty good at, but maybe it's worth going through one more time here, is how do I get the initial speed? Because coming back over to here, they gave me the whole speed, the 75. But I probably want to think about that, make a little triangle out of this, as this 75 at a 60 degree can be thought of as two speeds. One speed is how much along in the x direction, and the other speed is how much in the vertical direction. That way we get this little triangle here, and we can do something like cosine of 60 degrees is equal to initial velocity in the x direction over that total initial speed. And sine of 60 degrees is the opposite over the hypotenuse. And that way, with a little bit of math, we can get the initial speeds. So taking cosine of 60, which is 1/2, times 75 would make 37.5. Okay. And the sine of 60, which is at what, root 3 over 2, but 0.866, yeah, there it is. And then times the 75 make 64.95. All right, so maybe I'll just translate those onto this piece of paper. So 37.5 and 64.95. And then, like we've done so often with the projectile motion, let's write out the equation of position as a function of time. We called that equation number 2. And we'll do it for both x and y. And we'll fill in x first. So as we just said, the initial position is 0 and the acceleration is 0. So this becomes x equal 37.5 multiplied by t. And I'll circle it and call that my first equation. 2 unknowns. Okay, can't do much anymore with that. Let's jump over to here. Well, this would say y equals, and that first one is 0. Then this initial velocity in the y direction is 64.95. And this 1/2 of a negative 9.8 is a negative 4.9. And I guess I'll circle that one. And we've come into this problem a lot, that we would have two equations, but we would have two unknowns. Now we have three unknowns. So I'm thinking of like that soccer one, where they gave us the x and y. They didn't give us t. Oh, and they didn't give us initial velocity in that one. But bottom line is it was two unknowns with our two equations. But here we don't know x, we don't know y, and we don't know t. And so it's too bad we don't really know where it lands because it's somewhere on the hill. But clearly where it lands on the hill, someplace the x depends upon the y, and that's what this equation is saying. And so let me write down our third equation. This one is telling how us x and y's are related. And probably should just get a decimal out of this tangent of 20 degrees. So 0.364. And so now maybe it makes more mathematical sense that I've got three equations and three unknowns. And there's a lot of different ways of solving for this, and this could be a hard one. But I like this thinking. If I put x into here, then I would have y and t. And that's equal to a y, and that's equal to a y. So I could then set those two equal. And then I would only have t's and then t's. And I could solve for t. It does say where on the hill. So that alone, once I get time, won't help me. Then I need to use that to get x and y. But I can. Once I get the t, I can put it in here to get the x. I can put it here to get the y. So let's try that strategy. So let's put it into here, 0.364. And then I put in the x, which is 37.5 t minus 109. All right, so that is what I get putting those two together, and that's equal to y. And that's also equal to this, 64.95 t minus 4.9 t squared. And clearly then I have a quadratic equation. So there's a quadratic term, there's two linear terms, and there's a constant term. Let me kind of write them in the standard quadratic form. Moving into all to one side, I'll go over here to the left-hand side, so that becomes a positive. This one, it might be the harder piece. I got to put these together. So 0.364 times 37.5. So that's in front of that t, 13.65. And then I will subtract the 64.95. Okay, so minus 51.3 t minus 109. That then equals 0. So that's the only constant. Put those two together and over to here. All right. So there is my quadratic equation. And so I need to pull out the quadratic formula. Okay. So the opposite of b, and b is a negative 51.3, so that's going to come out to be a positive 51.3. b squared would be 51.3 squared, minus a 4. The a is 4.9, and the c is a negative 109. And then over to a. Now a, remember, is 4.9, so 2 times a is 9.8. And I'll just do an intermediate calculation. Since this is quite a bit right here, let me do the 51.3 squared. And it looks like that negative and that negative are going to ultimately make those two a positive, so I'll put plus. And then a 4 times a 4.9 times a 109. And then square root. And it looks like 69.05. Now, if I do both of these, you can see the one with the negative sign is going to give me a negative time, and then the positive one. And I guess we'll look at that and argue here which one we want. Hopefully it's obvious we want the positive, but let's talk. So I'll go the 51.3, and I'll go first plus the last answer, and then divide by 9.8. So we're looking at about 12.28 seconds, but also a 51.3 minus a 69.05, and I'm not sure if there's really any reason to calculate this one out, because we could argue that according to this whole system of equations, and maybe this will give me a chance to say it again, we're going to read the math, not just do it. But what does all this mean? And remember, t equaling 0 is where it starts. And so it obviously has to land at some time greater than 0. So that rules out the negative and gives me the positive. Now, if you're kind of wondering why there's 2 there, if you kind of extended this line and also extended the projectile motion, in other words, the projectile would continue. Now, in the real world, it would actually hit and stop. But if there was no hillside, it would continue like this. And see, that's how the math treats it. The math treats it as a constant acceleration. The math is just treating it as if it's acting by gravity, and there's nothing in our math that says it make an impact. So in terms of the math, we could get all of these, like we could say, you know, where is it after 100 seconds? And it would be way down here somewhere. So that's why I'm extending this, saying, look, even though it technically hits the hill right here, I would say that that's not represented in our math. Our math is saying what is the x and y at any moment in time, and including negative time. So if you said it was always under the effect of gravity, it would have to have come up to get to this point. And when it gets to this point, it must be going at 60 degrees and at a rate of 75. And then that's where we call time equals to 0. So all of this motion would be negative time, then it would get here, and then this would all be positive time. But do you see how it crosses this line? So there is a moment in time, negative time, where it crosses this line. And apparently that's the negative 1.8 seconds. So if it had been doing this motion for all times, both negatives and positives, it would cross this line twice. One time right here, which when it gets here, if we call that time equals to 0, this time must be 1.8 seconds earlier. So this solution has its usefulness. It's telling us that it would be crossing here. Although I might say it doesn't have any usefulness for this problem. But maybe the more usefulness is it gives me a chance to talk about, don't just do the math here, read the math. What are these things saying? This is our language of communication, reading the math. It becomes real powerful. And sadly, a lot of people can't read the math, and they give up, and they go, who needs math anyways, right? I can get by without it. And I suppose you can get by, but you could do a lot better if you could read math. Not just do math, but read math. So maybe this would help you read the math a little bit better, but I would argue that that's kind of pointless and not needed to solve this problem. It's more needed in an academic sense to say, what does it mean? How can this help me understand math better? And physics. Okay, so now as I'm doing the physics and reading the math, clearly I am wanting that for the time. All right. So to complete the problem, knowing that this is the time that I want, I could put it up here to get x. So 37.5 multiplied by 12.28 gives me a distance of 460, and I'll put a little line under it for 3 significant figures. I suppose we might argue it rounds up. 461 meters for 3 significant figures. So in this picture, the first 300 meters are a flat line, and so it goes another, it's like 161 meters along the sloping hill before it lands somewhere on the hill. And then up the hill, well, we could use this for time. We could also use this now that we know x. So kind of the choice is ours, and this one looks a little easier. So I'll do the y from this equation. And so that would be the 0.364 multiplied by the x. That's what I already have in my calculator. Then minus the 109. And so we would be about 58.6 meters up the hill. So again, if you went over 161, you're going to go up, what do we say, 58.6 meters. So that's where it hits on the hill. And no doubt, I see why it's in the challenging part of the advanced book. 3 equations, 3 unknowns is a little bit harder than the ones we've been seeing, which are 2 equations and 2 unknowns. All right, bye for now.